Alright, so this video is going to be about magnets and electricity. So, magnets are something that attracts iron-containing objects. They have a north and a south pole, and they really are kind of figured out depending on how they interact with the Earth and the Earth's magnetic field. And like electric charges, the poles of a magnet kind of operate the same way, where like poles of magnets repel each other, and unlike poles of magnets opposites attract in this case. Okay, so magnets are become magnetic when they have what these called these little regions of magnetism called magnetic domains. When all the magnetic domains align, an object is said to be magnetized. When they're not, it's not magnetized. Okay, and you can actually turn certain things into what are called permanent magnets, where they'll stay magnets. So a soft material like iron can easily be magnetized. So like a nail, you can actually magnetize like a nail. Nickel is hard to magnetize, but once you get it magnetized, it's really, really hard to unmagnetize it. This is an example of the domains. So unmagnetized, they are all over the place. All the arrows are pointing in random different directions. Magnetized, pretty much all of them are pointing in the exact same direction. So what this means is that the north pole of the magnet and the south pole of the magnets are all uniform, pointing in the same direction on these domains. Okay, so how do you magnetize objects to get those domains lined up? So you can bring a magnetic field, a area that has basically bring another magnet already near it, and to get the domains to line up. You can also have some electric current running through it, and so then the electrons are going to form a positive and negative end of the material, and then so you're going to magnetize it. So you can either bring another magnet near it, or make an electric current pass through it, because an electric current also has a magnetic field. Okay, so a magnetic field is simply a region in which a magnetic force can be detected. Okay, and they can be drawn with a compass, and they can look like this. Certain things to know about a magnetic field, as you can see, they make loops. Each loop is a magnetic field, and the more lines you have in an area, that's a stronger magnetic field. That actually indicates a stronger magnetic force at that part. Okay, and as you can see, the loops, they always will make closed loops, and the lines always go from the north pole of the magnet to the south pole of the magnet. Like the magnetic field around our Earth. Okay. Now, if you notice, because the compasses on Earth, the north poles point north, and because opposite poles attract, the north pole of your compass, of your magnet, actually points to the Earth's magnetic south pole. Okay, magnetic south pole, which is right near the geographic north pole. Okay, so yes, if the magnetic field of the Earth switches, your north part of your magnet will point south. It'll point towards the southern pole of the Earth's magnet. All right. So now, in a wire, you can actually have a magnetic field, or you do have a magnetic field when you have a wire that has electric current passing through it. Okay, and a long straight current carrying wire has a cylindrical magnetic field, which means there's like a tube around the wire from a magnetic field, but it's always pointing perpendicular to the way the current travels. Okay, and you can use a compass and what's this called, the right hand rule, you don't have to worry about that, to show that the magnetic field points in a perpendicular direction. And we have this. Okay, I is your current. Okay, B is your magnetic field. Now, if you look at B, even though it's going in a circle, it goes perpendicular to the way that your current is traveling. That's the main thing. The magnetic field that's created by this wire, by the current in this wire, goes perpendicular to the direction of the charge. Okay, and again, same thing. When there's a current, all these are lined up perpendicular to the wire. Zero current, they all point in the direction of the Earth's magnetic field. Okay. Now this is called a solenoid. Okay, a solenoid is instead of taking one coil of wire, you take multiple coils of wire and you run electric current through it. Like I said, I is your electric current. So if you notice, there's all these loops that follow this same idea that they make one loop on the wire, except now you bunch all these coils together and you make a much, much stronger electric field. Okay. So a solenoid is a coil of wire that has electric current running through it that makes a strong electric charge, magnetic charge. Okay. So current carrying wire undergoes a magnetic force. Okay, so if you bring a wire near a magnet, there's going to be a magnetic force acting on it. Okay, because moving electrons make a magnetic force, make their own magnetic force. So if you have electrons that are already moving on a wire, and they bring it near a magnetic force, you have two magnetic forces that are acting on each other. So again, when a charged particle is moving, it creates a magnetic field. And that magnetic field is created in a direction perpendicular to the direction of the motion of that charged particle, as shown with the previous pictures that I showed you. All right, so now we're going to look at something called electromagnetic induction. Okay, it's the process of creating a current in a circuit by changing the magnetic field that it's in. Okay, that magnetic field is really what's called the magnetic flux. Okay, and a change in this magnetic flux, this magnetic field area, makes current go through a conductor. Conductors are something that moves electric charge through it. Okay, and the separation of charges by the magnetic force, so if making things separate, induces a potential difference of voltage. Okay, I'm going to show you a little video here from a simulation. Okay, so this magnet has a magnetic field. That's what these field lines are. We have wires that are running onto this coil. This is simply a coil of wire with a light bulb, and this voltage shows a potential difference. Now, if I don't move my magnet through this coil, nothing happens. We get a little bit of charge up here as the magnetic field changes in the coil. Now watch, if I take it and I make it go through the middle, I can get a big change in voltage. Okay, I can get a big change in voltage as I take these magnetic field lines and run them through the coil of wire. Because what's happening is these magnetic field lines are pushing around these electric charges to give it a potential difference to make the charges move through. Okay, now we can also show that if I take this magnet and run it through a little coil of wire, I can get, watch the voltage up here, I can get a little bit of voltage to happen. However, if I take it and I run it through a higher coil of wire, I get a bigger voltage. Okay, so the more coils of wire, the greater the potential difference. That's an important piece of information. Okay, so kind of a drawing of what you saw. So the blue is your magnetic field. The square is like in this case, it's a wire being passed through this magnetic field. So it's kind of the opposite of the simulation that you just saw. And the angle that these wires and magnetic fields interact are crucial, because the more magnetic field lines, which are these blue things, this square goes through, the stronger the force acting on it, the stronger the current passing through this little square will be. Okay, so like this way for A, when it's going in a direction that it can actually cross over a lot of these, you're going to have a big induction, a big electromagnetic induction, a big what they call electric flux on this wire. However, unlike C, where it's lining up just a little bit, there's not as much flux because it's not going through as many lines. Okay? So that's a big thing, that the flux really deals with the number of parts of the magnetic field that it goes through. The more areas of the field that the wire goes through, the more that current wants to be pushed, more that magnetic field pushes the electrons in the wire, the greater the potential difference. Okay, we're going to watch a little video clip here.
This square of wire represents a closed circuit. Current can be induced in a closed circuit in 3 ways. One method is to move the circuit into or out of a magnetic field. Note that the induced current is 0 except when the circuit is entering or leaving the field. A second method is to rotate the circuit in the magnetic field, thereby changing the angle between the area of the circuit and the magnetic field. The third method is to change the intensity of the magnetic field itself. The induced current is proportional to the rate of change of the magnetic field intensity.
So I would play that again and rewatch it. In fact, we're going to.
This square of wire represents a closed circuit. Current can be induced in a closed circuit in 3 ways. One method is to move the circuit into or out of a magnetic field. Note that the induced current is 0 except when the circuit is entering or leaving the field. A second method is to rotate the circuit in the magnetic field, thereby changing the angle between the area of the circuit and the magnetic field. The third method is to change the intensity of the magnetic field itself. The induced current is proportional to the rate of change of the magnetic field intensity.
So it's all about changing how much the magnetic field interacts with this electric wire.
Lenz's law states that the magnetic field of an induced current opposes a change in the applied magnetic field. If the applied magnetic field is in motion, as in the case of a moving bar magnet, the induced magnetic field points in a direction opposite to the applied field's direction of motion. When the motion of the applied field stops, the magnetic field of the induced current falls to 0 because the value of the current is 0. When the motion of the applied field reverses direction, the induced magnetic field reverses direction as well.
So the magnetic field that's created on this wire is opposite of the direction that magnet traveled. Okay, so the magnitude of this potential difference, often called an induced EMF, is known as what's called Faraday's law of magnetic induction. Okay? And that magnetic flux, this voltage, this magnetic flux, this change in magnetic field, is shown by this formula. Now this is called phi. Phi m equals, yes, it says NBA. However, phi is m, which is called flux. Flux just means change. Now this, with the m here, this is magnetic flux. And the unit of flux is actually the Weber. W-E-B-B-E-R. So that's your magnetic flux. N is the number of coils in the wire. As you saw with those videos, there always has to be a coil of wire that the magnet has to travel through. B is the magnetic field strength. So like when the magnet passes through that wire, that magnet has a certain magnetic field, and that can be measured in Tesla. And A is the area of wire going through the field. Okay? So those are your variables here. So you can see the greater number of coils, the greater the flux, the greater the change in magnetic field, the greater the field strength change. Okay? So they're all directly related to the flux. They're indirectly. So as one goes up, the other goes up. Okay, so this is another way to write the same formula. Okay, this talks about what Faraday's law is. A coil moving into a magnetic field is one example of an EMF of potential difference, according to the Faraday's law. So the current induced in this wire will create a magnetic field that opposes the magnetic field of the coil. So this magnetic field opposes where these electrons are and cause the electrons in there to move, inducing a current. Okay, and Faraday's law, this EMF is really a voltage. So EMF is voltage is equal to the number of turns times phi. Remember, phi is BA, the number of what's your magnetic flux, okay, which is your magnetic field and the area divided by how long it takes to go through. So your voltage is really a key part of how fast you go through. If you go through this if you take a long time, you don't have as big of a voltage because you have a big number on the bottom. You go through in a quick time, you have a big voltage, a big change in your flux, a big change in how the field on your object. Okay. Another way to look at it is look at it on a graph. Okay, because if you think back to the formula here, the voltage is how fast you change your flux. Okay, so on a flux versus time graph like the one on the right, the slope of this line times the number of coils gets you the voltage through the wire. Okay, so if you can figure out the flux, which is Teslas times meters squared, magnetic field times the area of your wire, times your time, divided by your time gets you your slope, your flux divided by time, times your number of coils gets you your voltage. Okay. So, if this graph shows a flux time versus time graph of a wire that has 5 coils, we're going to look at what the voltage is for this first 2 seconds. Okay. So the slope from t equals 0 to t equals 4, or t equals 2, is 4 Teslas because it goes up. It goes up 8 and over 2, which is 4. Rise over run is 4. Okay? So the voltage is the number of coils times the slope. So the number of coils is 5 times my slope, which is 4. 5 times 4 is 20. Okay? So right here from 2 to 4, there is no potential difference. There is no voltage because the flux remains constant. Now we're going to do a problem. And you might have heard of MRIs. Okay? We're going to look at the magnetic field, how strong the magnetic field is inside a coil of an MRI. Okay? So an MRI, this particular MRI has a large electromagnet, a wire around a magnet that has an area of 0.5 meters. There's a flux of 0.29 Webers that passes through it. We're going to find the strength of the magnetic field inside the coil. So it's one coil with an area of 0.5 meters with this big of a flux passing through it. Okay, so our formula, phi equals NBA. N is one coil, B we don't know, A is a half a meter squared, and your flux is 0.29 Webers. So if we put the numbers into the equation, 0.29 equals 1 times B times a half. Okay, remember this time we're just squaring the unit, so it's not 0.5 meters squared. Okay, so to solve for B, it would be 1 times 0.5, which is 0.5, and then take 0.29 divided by 0.5 to get B by itself, and B is 0.5 or 0.58 Tesla, which is your magnetic field strength. Okay, that is the end of this video. Make sure to answer the questions on the Google form, and we'll see you in class.